Bonding part 15. Now, we're now looking at metallic bonding. Metallic bonding is the bonding that occurs within pure metals. So for example, let's say iron. If you could zoom into a piece of iron, what you would see is, you would see the nuclei of the iron atoms. So basically the stuff that contains the protons and the neutrons. Now the neutrons don't have a charge, but the protons are positive. So the overall charge on any nucleus is positive. So in metallic bonding, this is what we have. We have atoms, or the nuclei, I should say, in nice, neat rows, and they're positive. What you also have is a sea of electrons. We call them delocalized electrons. Think about the word delocalized. So not local, not like in a particular area. They can basically move around. Now, what actually causes then the atoms to sort of stick together? What keeps metallic bonding together? This is often a bit that people don't really recognize. It's the attraction between the positive nuclei and the electrons. So the attraction between the positive nuclei and the electrons is what keeps this together. This also then means that in metallic bonding, that actual force between them is strong. So they have high melting points and high boiling points. They can also conduct electricity because of the sea of electrons. So the electrons mean that they can conduct because the electrons can move. And then finally, metals are malleable. They are malleable means they can be bent into different shapes. So if you could picture a piece of iron, all the atoms look like this in nice neat rows. So if you had like a hammer and you was to whack the atoms, they can slide past each other. That's what makes metals malleable. So three key things is metallic bonding results in high melting points and boiling points because the attraction between the ions and electrons is strong and requires lots of energy to overcome. In metallic bonding, you can conduct electricity because the electrons are delocalized. And in metallic bonding, or metals in general, are malleable because if you used to hammer them on the side, the atoms would slide past each other.